Okay, in this next problem, we have a table of values for time and velocity. The velocity of a particle moving along the x-axis is modeled by a differentiable function v, where position x is measured in meters and time t is measured in seconds. Selected values of v of t are given in the table above. The particle is at position x equals 7 meters when t is equal to 0. And the first thing that we want to do is to estimate the acceleration of the particle at t equals 36 seconds. And since we don't have a function for velocity, we're going to have to use this secant line approximation method that we've done before. And it's explained in depth in a previous problem. So I'm just going to go ahead and work this out. And t equals 36 lies in between t equals 32 and t equals 40. So we're going to do a secant line. We're going to find the slope of the secant line between points 40, 7 and 32, -4. And so that comes out to be 7 minus -4, which is 11, over 8. And the units of measure for this are going to be meters per second. And it's meters per second because we are estimating the velocity. Now, part B, we want to, using correct units, explain the meaning of the integral from 20 to 40 of v of t dt in the context of this problem. So the integral from 20 to 40 of v of t dt quite simply is going to give the change in position from time t equals 20 to t equals 40 in meters. A definite integral gives you a change in the underlying function. So if v is the derivative of position, then the integral of v over a given interval of time is going to give us the change in position over that time. Now, second, we want to use a trapezoidal sum with 3 subintervals indicated by the data in the table to approximate integral from 20 to 40 of v of t dt. Now, the first thing you have to understand here is that we're not looking for the integral from 0 to 40. We're only working from 20 to 40. And that's not meant to trick you, but it's just that it would be that much more calculations involved, and they want to know that you understand how to do it without giving you too much to do in the meantime. So, but you have to read these problems very carefully because you can't assume that it's asking over the entire interval. So we have these 3 intervals from 20 to 40, from 20 to 25, that has a width of 5, from 25 to 32 has a width of 7, and from 32 to 40 has a width of 8. Now once again, you can make a graph of this, but sometimes when the points are positive and negative, it could cause some confusion when you're looking at a picture of what's going on here. So I'm still going to suggest that you learn to do this by the numbers and try to get away from the time that you're going to spend to create a graph of this. Now, this is all based on the fact that the area of a trapezoid is given by h over 2, the height of the trapezoid over 2 times the sum of the bases, or it's the height times the average of the 2 parallel bases. What you have to realize when we're working with calculus is that our trapezoids, which we're familiar working with them in this shape, in calculus they're going to be more like this. And so the bases, the parallel bases, are now the heights actually, and the height is actually the perpendicular distance between the parallel bases, which is going to be the width of the subintervals here. So in this particular case, the height for subinterval 1 is 5, for subinterval 2 is 7, and for subinterval 3 is 8. And the sum of the bases in the first interval is going to be -18, in the second -12, and in the third 3. So putting that all together, we get the integral from 20 to 40 v of t dt is approximately 5 over 2 times -18, 7 over 2 times -12, 8 over 2 times 3, which is -45 minus 42 plus 12, or 75 meters. We'll continue in the next video.